Okay, so in this video, we want to find the area of the region bounded by the curves x equals negative 2y plus 7 and x equals y squared minus 1. Now this is the first time that we are given curves in the form of x being a function of y in both cases. And I know that some of you may not be comfortable sketching curves given in this form, so for now we'll bite the bullet. We'll do it as is, but then I'll show you a very simple and intuitive geometric idea that will allow you to convert everything back into y being a function of x, so that sketching the curves is more intuitive. And it won't just be an algebraic method as, well, in the equation just solve for y back as a function of x, right? Here, if you did this here, you'd get x plus 1 is y squared, and so y would be plus or minus the square root of x plus 1. And this is very unpleasant. You're much better off with an equation like this with no square roots. And I'll show you when we're done with this problem as is, a very nice geometric idea that will allow you to rewrite each curve as y being a function of x, with the equations being essentially unchanged. And so that way, given y being a function of x, it should be more intuitive and you should have an easier time sketching the curves. But now let's do it directly. So we'll find the points of intersection between these two curves, so we'll equate the x's, and so y squared minus 1 equals negative 2y plus 7. As always, send everything on one side, so you can look at the zeros of a polynomial. And as always, we try and factor by inspection. So we have a quadratic. We're looking for two real numbers whose product is negative 8 and whose sum is positive 2. This is of course negative 2, positive 4. Negative 2 plus 4, positive 2. Negative 2 times 4, negative 8. And so our two zeros, y equals 2 or y equals negative 4. But we want the full coordinates of our points of intersection, so let's see what we have. The x and the y coordinate, x and the y coordinate. So y equals 2, y equals negative 4. What is x? Well, let's go back to the curves, and you can take either curve as these 2 points are on both curves. So let's take this one. We square y and we subtract 1 to get x. 2 squared is 4 minus 1 is 3. Square this, you get 16 minus 1, you get 15. And now we have our 2 points of intersection. And you can double check to see if these points are also satisfying this equation. Right? If you do negative 2y plus 7, will we get x? So negative 2 times 2 is negative 4 plus 7 is 3, check. Negative 2 times 4 is 8, plus 7 is 15, check. So these are the 2 points of intersection. And now we can sketch these curves with the help of our points of intersection. Let me just rewrite the curves here. So x equals negative 2y plus 7. X equals y squared minus 1. So if you look at our points of intersection, we have the point x equals 3, y equals 2, so somewhere here. And then we have the point x equals 15, negative 4, so somewhere here. Well, you can sketch the easier curve first. This is simply a line. It's a line of negative slope, and it passes through this point and this point. So it's going to look something like this. Our line x equals negative 2y plus 7. And this is now a parabola. X is given as a quadratic function of y. And if you think of it, well, will it be going like this or going like this? Well, as y goes to positive or negative infinity, y squared goes to positive infinity, so the parabola must go like this. And if you look at your points of intersection, it's somewhere here and somewhere here. So it will look something a little bit like this. Very rough sketch, but as long as it's fairly accurate with the points of intersection, we're okay. So for this point, this was clearly 3 for x, 2 for y. So x equals 3, y equals 2. And the second point of intersection, x equals 15, and y was negative 4. You can see my picture is clear enough up to scale, it doesn't matter. As long as you have a good enough sketch of the region, you can find its area. If this would have been a negative y squared, our parabola would have been going like this. So it's always very simple, right? If x is a positive quadratic in y, it will look something like this. If x is a negative quadratic, it would look something like this. So now that we have the region, right, we can see that the region bounded by our two curves is clearly this region, and we want to find its area. As always, we have to ask ourselves one question. Do we use vertical or horizontal rectangles? Well, if you think here of a vertical set of rectangles, this is a very bad idea, right? If you have a vertical rectangle here, the height will be the value of y on this curve minus the value of y on this curve, which is the same curve. And as you go beyond 3, now the curve on top changes, right? Below 3, the curve on top is the quadratic. To the right of 3, the curve on top is the line. So this will once again force you to have two different integrals. And at this point, if you check, when y is 0, if I just go up for a second, when y is equal to 0, x is negative 1. So at this point, the x value is negative 1. But the point is, if you go with vertical rectangles, as the curve on top changes from negative 1 to 3, it's the quadratic. From 3 to 15, it's the straight line. This will force you to have two different integrals. This one won't be too bad. This one will be very unpleasant in terms of finding the two y values on the same curve. So you say, alright, well let's see with a set of horizontal rectangles. If we go with a horizontal rectangle, then the height, the length of the rectangle is going to be the bigger x value minus the smaller x value. Therefore, the curve on the right minus the curve on the left. But the curve on the right will always be the straight line. The curve on the left will always be the quadratic. So here with a set of horizontal rectangles, we will find the area from a single definite integral. So we go with horizontal rectangles. So the width is a small change along the y-axis, so it is dy. The position is at y, and we now need the length of the rectangle. This is a segment along the x-axis, so we need both x values at endpoints of our rectangle. And this is already given. At the right endpoint, x is negative 2y plus 7. And I forgot to rewrite the equation here, but this was x equals y squared minus 1. So at the left hand point of the rectangle, we are on the quadratic, where x is y squared minus 1. And so the height or the length of the rectangle is the bigger x value, negative 2y plus 7, minus the smaller x value, which is y squared minus 1. If we simplify, of course, we'll get negative 2y, negative y squared, sorry, and 7 negative negative 1 is 7 plus 1, which is positive 8. So now we have the height of our rectangle. Now we're essentially done, right? The area of one of our horizontal rectangles is the height times the width dy. So negative 2y, negative y squared plus 8 times dy. That is the area of one rectangle. To get, again, the total area of our region, we must add the area of all the rectangles. We must sum them. Sum from where? Well, we are summing along the y-axis, and our rectangles begin at y equals negative 4, and they go all the way up to y equals 2. And now we're good to go. If we evaluate our integral, we'll get the area of this region. As our function is a polynomial, this would be very easy to do. So of course we use first the fundamental theorem of calculus. We find an antiderivative. We'll have negative 2y squared over 2. The 2 over 2 will cancel, which will leave us with negative y squared. Minus power rule y cubed over 3. Positive 8y. And we evaluate this from negative 4 to 2. And now we just plug it in. Replace y by 2. So negative 2 squared is negative 4. Negative 2 cubed is 8 over 3. So negative 8 over 3. Plus 8 times 2 plus 16. So our antiderivative at 2, of course, minus the antiderivative at negative 4. Negative 4 squared is 16. We negate that, we get negative 16. Negative 4 cubed is negative 64, but we negate that, so we get positive 64 over 3. Negative 4 times 8, negative 32. And now we just simplify. So let's see, negative 4 plus 16 gives you positive 12, minus 8 over 3. Here what do we have? Negative 16, negative 32, that's negative 48, but we negate that, so we get positive 48, and negative 64 over 3. Let's combine the integer values. 12 plus 48 is 60. And if we combine the fractions over 3, we get negative 8, negative 64. That's negative 72 over 3. But 3 times 24 is 72. So all we're left with is 60 minus 24, which is 36. So the exact area of the region bounded by the curves x equals y squared minus 1 and x equals negative 2y plus 7, so this region right here, is exactly 36 units squared. So there you go. But now I want to go over the problem and addressing the question that I know that some people will be uncomfortable sketching curves in the plane when they're given as x being a function of y. And this is reasonable because we're so used to seeing a curve given by y equals f of x that once we see x being a function of y, it kind of throws us off a little. So how could we be smart about this and be able to convert back both to a function of y being a function of x? The idea is, what if we were to make a reflection in the xy plane about the line y equals x? If we have a region anywhere in the xy plane, and we reflect about any line, the region will be positioned in a different way, but it will still be preserved, it will still be intact, and so the area of the region will not change. And so the idea is, if we reflect our region about the line y equals x, the region will be flipped like this. It's just a reflection, but a reflection preserves the shape of objects, so the reflected image of the region will have the same area. But if you remember, when you reflect about the line y equals x, what you do is you change y for x and x for y. Because if you reflect about the line y equals x, the x-axis after the reflection will land onto the y-axis, and the y-axis will land onto the x-axis. So once you perform this reflection about the line y equals x, which will not change the area of the region, y becomes x and x becomes y. So all you have to do is change y for x and x for y. And let's see what that gives us. So the two curves initially were given in the form of x being negative 2y plus 7 and x being y squared minus 1. Now if we perform a reflection about the line y equals x, y becomes x, x becomes y, so x becomes y, so y will equal, and y becomes x. Negative 2x plus 7. And here, x becomes y, y equals, y becomes x. X squared minus 1. And so you see, if you're ever given curves in the form of x being a function of y, just change all of the x's for y's, all the y's for x's, and now, instead of finding the area of the region bounded by these two curves, find the area of the region bounded by these two curves. As quite simply, the resulting region is the same as this one once it is reflected about this line. But the area will stay the same, as the reflection preserves the figure, therefore preserves its area. So let's just go quickly over this to see that we get the same region. Let's look at the points of intersection now. We'll equate the y values. So x squared minus 1 equals negative 2x plus 7. Send everything here on the left, you'll get x squared plus 2x minus 8 equals 0. This factors as x minus 2 times x plus 4. So x equals 2 is one solution. X equals negative 4 is another solution. We want the points of intersection, so we need the corresponding y coordinates. When x is 2, y is 4 minus 1, 3. When x is negative 4, y is 16 minus 1, 15. So we have our new points of intersection. And now this is more intuitive. Y is a function of x, which is a line of negative slope. And this is just y equals x squared minus 1, which again looks much more familiar. So if you sketch the region, let me sketch it here. This is just y equals x squared, but shifted vertically down by 1 unit. And this is a line of negative slope. Y equals negative 2x plus 7. So it would look something, I'll go a little higher. Negative 2x plus 7 is something like this. These are aligned with negative slope. So y equals negative 2x plus 7. And we have our points of intersection. X equals 2, y equals 3. And the other point, x equals negative 4, y equals 15. And now you can find the area of this region, of course, quite easily by setting up now vertical rectangles. The width is dx, small change along the x-axis. The height of the rectangle, well, now the height is a segment along the y-axis, so we need a bigger y value here. Y is negative 2x plus 7. and the smaller y value here, which is x squared minus 1. And so the height is of course the larger y value minus the smaller y value. I guess I should have put it here. But if you do this minus this, you'll get negative 2x. Negative x squared. 7 minus negative 1 is plus 8. And now you have the height of the rectangle. And now we're essentially done. The area of this rectangle is the height times the width. So negative 2x, negative x squared, positive 8, dx. And we have to sum the area of all these rectangles along the x-axis. But our rectangles along the x-axis span from x equals negative 4 all the way up to x equals 2. And that gives us the area of the region. And of course, if you evaluate this, you will get the same as before, 36. And now let's just look back to what happened, right? We were given the curves, x as functions of y's. We're not happy with this. We perform a reflection about the line y equals x, so we change all the y's for x's, all the x's for y's, and now the curves are much more familiar, and it should be easier to sketch the region. And let's see that we get the same problem. Let me put the two regions next to one another, right? So here's the original region, and you see if you do reflect, if I draw the line y equals x, if I do perform the reflection of our region about the line y equals x, this will be flipped, and you get exactly this region. It's just the same region, except it's positioned differently in space. What this gives you, though, is a way to have curves given as y equals f of x, which is more familiar, and it should be easier to sketch the given curves. And now let's compare the two integrals to see that we will get the same area. So look, this is the original integral as a function of y. This is the new integral as a function of x after we perform the reflection. And you get to integrate from negative 4 to 2, negative 4 to 2, negative 2x, negative 2y, negative x squared, negative y squared, positive 8, positive 8, dx, dy. And so you see you get the exact same integral. The only difference is the y's are now all x's. So you can see it really is the exact same problem. And so I leave you with this. If you are ever given curves in the form of x equals a function of y, and it confuses you, no problem. Change all of the x's for the y's and all the y's for the x's, and all this will do is reflect the region about the line y equals x, but the region is still the same, it's just positioned differently in space, and therefore has the same area. And this problem should be easier, as y is now a function of x, which should be more familiar. And that's it.